All right, so today we're going to do something a bit different. We're going to take a real GCSE chemistry question and completely deconstruct it. The goal here isn't just to get the right answer, but to figure out exactly how an examiner thinks, how they award every single mark according to the official guide. Ready? Let's jump right in.
So here's the game plan. First, we'll get a handle on the experiment itself. Then we'll look at the easy marks, the procedure and safety stuff. After that, it's time to crunch some numbers from the data. And the big one, using those numbers to figure out the right chemical equation. Finally, we'll zoom out and see what all this tells us about how to absolutely nail these questions.
And that's the key, isn't it? That's the real puzzle. You can know all the chemistry in the world, but if you don't explain it in the very specific way the examiners are looking for, you won't get the marks. It's all about communication. Stick with me and you'll see exactly what I mean.
Okay, let's set the scene. Imagine you're in an exam and you get this question. A teacher is trying to figure out the formula of an unknown copper oxide. The experiment's pretty cool. They heat it up in a stream of hydrogen gas. What happens? Well, the hydrogen basically rips the oxygen away from the copper, forming water, and leaving behind pure, shiny copper. And our mission is to use the data to work out what that original copper oxide was.
Right, so before we even touch a calculator, there are some marks on the table. These are for the basics, understanding the how and why of the experiment, and especially the safety stuff. Honestly, these are often the easiest points you can get, as long as you know what they're looking for.
First question up. It's about a classic lab technique, one you see all the time, heating something to a constant mass. So, step 8 in the procedure says to repeat the heating and weighing steps over and over until the mass stops changing. Why bother? What's the point of doing that?
Okay, let's peek behind the curtain at the official mark scheme. It actually gives two perfectly good answers here, and either one gets you the mark. You could say it's to make absolutely sure that all the copper oxide has reacted. Or you could say it's to make sure all the water that was produced has been boiled off. See? Both answers show you get the main idea. You're waiting until the reaction is completely finished and the mass is stable.
All right, next part is all about safety. So in this experiment, we've got a constant stream of hydrogen gas flowing through everything. But not all of it reacts. The extra gas comes out the other end, and the instructions say you have to burn it off with a flame. So why is that so important? Why not just let it float away?
Now, first thing to notice, this is a 2-mark question. That's a huge hint. It means you need to give 2 separate but connected reasons. For the first mark, you just need to say what you're doing. You're stopping the hydrogen from getting out into the room. Simple enough. But for the second mark, you have to explain why that's a problem. And the key word is because hydrogen is explosive. You've got to have both of those points to get both marks.
And here's a fantastic little detail that shows you exactly how precise you need to be. In the notes for the examiner, the mark scheme literally says, ignore hydrogen is flammable. Now, hang on, is hydrogen flammable? Of course it is, but that's not specific enough. The real danger here isn't just that it can catch fire, it's that it can mix with the air and create an explosion. So flammable gets you 0 points. Explosive gets you the mark. That one word makes all the difference.
Okay, enough with the theory for a minute. Let's get to the fun part, the numbers. It's time to take the raw data from the experiment and actually make sense of it. So, here are the results from the teacher's experiment, laid out in a table. Just to recap, 2A is where the reaction happened. It started with the copper oxide. 2B was there to catch all the water that was made. And our job is to use these starting and ending masses to figure out how much copper and how much water were produced.
The question itself is super straightforward. All it's asking is, determine the mass of copper and the mass of water. That's it. This is purely a test of whether you can read a table and do some simple subtraction.
Unfortunately, the data in the table provided in the prompt is incomplete to solve the question. The question paper gives the mass of empty tube A as 105.72 grams. So after the experiment, the tube plus the copper weighs 114.38 grams. To find the mass of the copper, we just subtract the mass of the tube itself. And what we're left with is 8.66 grams. Boom, first answer done.
Okay, what about the water? That's even easier. Remember, 2B's only job was to soak up the water produced, so all we have to do is see how much heavier it got. We take its final mass, 123.38 grams, and subtract its starting mass, 120.93 grams. The difference is, that's the mass of the water, 2.45 grams. Just like that, another 2 marks in the bag.
All right, and now for the grand finale, the main event. This is where we put everything together. We're going to use a new set of data and some core chemistry ideas to finally solve the big mystery. What was that copper oxide?
So, the question gives us some fresh numbers from a different run of the experiment. This time, they made 2.54 grams of copper and 0.72 grams of water. Our challenge is to use these numbers and our trusty periodic table to choose between two possible equations. Was the original stuff Cu2O or was it CuO? Let's find out.
Okay, whenever you're trying to find an equation from masses, there's one word you need to think of: moles. We have to find the mole ratio. Step 1. Moles of copper. We take the mass, 2.54 grams, and divide by the atomic mass of copper, which is 63.5. That gives us 0.04 moles. Step 2. Moles of water. We take its mass, 0.72 grams, and divide by the MR of water, which is 18. And what do you know? We get 0.04 moles again. So the ratio of copper to water is 0.04 to 0.04, which is just a simple 1-to-1 ratio. Now we look back at our two equations. Which one has a 1-to-1 ratio between Cu and H2O? It's equation 2. That's it. That's our answer.
But wait, there's more. And this is what's so cool about a really good mark scheme. It knows there isn't always just one right way to solve a problem. It's not about memorizing a single method. It's about showing you understand the chemistry no matter how you get to the answer. Check this out. The official mark scheme actually lists other ways you could have solved this and still gotten full credit. For instance, you could have worked backwards. You could have said, okay, let's pretend equation 1 is right. If I make 0.72 grams of water, how much copper should I get? You do the math and the answer wouldn't be 2.54 grams, but then you tried for equation 2 and bingo, it would match perfectly. All of these different paths are totally valid and show you know your stuff.
So, we've just spent all this time tearing apart a single exam question. What's the big takeaway? What are the secrets that the mark scheme has revealed about what examiners are really truly looking for?
Well, it really comes down to a few key things. Number 1, precision matters. A lot. Remember the whole explosive versus flammable thing? One word can be the difference between a mark and nothing. Number 2, show your work. Every step of a calculation is a chance to earn points, even if you mess up the final answer. Third, it's about applying those big ideas, like using moles to connect mass to an equation. And finally, it's all about your logic. The mark scheme isn't rigid. As long as you can show a clear, logical path to your answer, you're going to get the credit.
See, learning how to read a mark scheme isn't about gaming the system. It's about learning the language the examiners speak. It's about understanding the rules of the game so you can show them what you actually know. You now have the inside track, so the only question left is, what problem are you going to solve next?